Hello friends, welcome to this YouTube channel. Today we are going to solve one numerical problem on three-phase medium length transmission line. By solving this problem, we shall learn how to determine voltage regulation of a three-phase medium length transmission line using its nominal T equivalent circuit when load details and values of transmission line parameters are given. A three-phase 50 Hz 100 km long overhead transmission line with 132 kV between lines at the receiving end has the following constants. Resistance per phase per kilometer equals to 0.15 ohm. Inductance per phase per kilometer equals to 1.2 millihenry and capacitance per phase per kilometer equals to 0.01 microfarad. Using nominal T representation, we have to determine the sending end voltage and current, the sending end power factor, and the percentage voltage regulation when load at the receiving end 72 megawatts at 0.8 power factor lagging. Let us first write down the given data. Power delivered to the load PL equals to 72 megawatts, that is equal to 72 into 10 to the power 6 watts. Line to line receiving end voltage VL line equals to 132 kilovolts, that is equal to 132 into 10 to the power 3 volts. For star connected system, receiving end voltage per phase VR equals to VR line divided by root 3, that is equal to 132 into 10 to the power 3 divided by root 3, that gives us 76,210 volts. Given load power factor cos phi L equals to 0.8 lagging. Let us now calculate power factor angle. Phi L equals to cos inverse 0.8, that is equal to 36.8699 degree. Expression for power delivered to the load PL equals to root 3 times VR line into IL cos phi L. Therefore, load current IL equals to PL divided by root 3 times VR line into cos phi L. Using values we get 72 into 10 to the power 6 divided by root 3 into 132 into 10 to the power 3 into 0.8, that gives us 393.65 ampere. Load current may be written in polar form as IL equals to IL at an angle minus phi L, that is equal to 393.65 ampere at an angle minus 36.8699 degree. Given length of the transmission line D equals to 100 kilometers. Resistance per kilometer per phase R1 equals to 0.15 ohm. Inductance per kilometer per phase L1 equals to 1.2 millihenry and capacitance per kilometer per phase C1 equals to 0.01 microfarad. Now we shall calculate resistance per phase. R equals to R1 times D. Using values we get 0.15 into 100, that is equal to 15 ohm. Inductance per phase L equals to L1 times D. Using values we get 1.2 into 100, that is equal to 120 millihenry, that is equal to 0.12 Henry. and capacitance per phase C equals to C1 times D. Using values we get 0.01 into 100, that is equal to 1 microfarad, which is equal to 1 into 10 to the power minus 6 farad. Inductive reactance per phase XL equals to 2 pi F into L. Given supply frequency F equals to 50 Hz. Therefore, XL equals to 2 pi into 50 into 0.12, that is equal to 37.7 ohm. And capacitive susceptance per phase Vc equals to 2 pi F into C. Using values we get 2 pi into 50 into 1 into 10 to the power minus 6, that is equal to 3.1416 into 10 to the power minus 4 mho. Transmission line impedance per phase Z equals to R plus JXL, that is equal to 15 plus J times 37.7 ohm. Now we shall determine per phase impedance of half of the transmission line. ZH equals to half of Z, that is equal to 7.5 plus J times 18.85 ohm. This may be written in polar form as 20.287 ohm at an angle 68.3 degree. Taking receiving end voltage per phase as reference, we can write VR equals to 76,210 volts at an angle 0 degree. We have computed load current IL equals to 393.65 ampere at an angle minus 36.8699 degree. This may be written in Cartesian form as 314.92 minus J times 236.19 ampere. Per phase impedance of half of the transmission line ZH equals to 20.287 ohm at an angle 68.3 degree, and capacitive susceptance per phase Vc equals to 3.1416 into 10 to the power minus 4 mho. Let us now calculate capacitor voltage per phase. Vc equals to VR plus IL into ZH. Using values we get 76,210 at an angle 0 degree plus 393.65 at an angle minus 36.8699 degree into 20.287 at an angle 68.3 degree. That gives us 83,024.27 plus J times 4,164.36 volt. This may be written in polar form as 83,128.643 volt at an angle 2.87 degree. Now we shall calculate capacitor charging current. IC equals to Vc into J times Bc. Using values we get 83,128.643 at an angle 2.87 degree into 3.1416 into 10 to the power minus 4 at an angle 90 degree. That gives us 26.1157 ampere at an angle 92.87 degree. This may be written in Cartesian form as minus 1.3076 plus J times 26.083 ampere. Sending end current Is equals to Ic plus IL. Using values we get 313.6124 minus J times 210.107 ampere. This may be written in polar form as 377.5 ampere at an angle minus 33.82 degree. Let us now determine sending end voltage per phase. Vs equals to Vc plus Is into Zh. Using values we get 83,024.27 plus J times 4,164.36 plus 377.5 at an angle minus 33.82 degree into 20.287 at an angle 68.3 degree. That gives us 89,337.224 plus J 8500 volt. This may be written in polar form as 89,740.68 volt at an angle 5.435 degree. We have computed sending end voltage per phase. Vs equals to Vs at an angle delta equals to 89,740.68 volt at an angle 5.435 degree, and sending end current Is equals to Is at an angle minus phi 1 equals to 377.5 ampere at an angle minus 33.82 degree. For star connected system, line to line sending end voltage Vs line equals to root 3 times Vs, that is equal to root 3 into 89,740.68. That gives us 155.435 into 10 to the power 3 volt or 155.435 kilovolt. Phase difference between Vs and Is, phi s equals to delta plus phi 1. Using values we get 5.435 degree plus 33.82 degree. That gives us 39.255 degree. Now we shall calculate sending end power factor. Cos phi s equals to cos of 39.255 degree, that is equal to 0.7743 lagging. Let us remove the load from the receiving end and calculate capacitor charging current. ICO equals to Vs divided by Zh minus J times Xc. We have computed sending end voltage per phase. Vs equals to 89,740.68 volt at an angle 5.435 degree. Per phase impedance of half of the transmission line Zh equals to 7.5 plus J times 18.85 ohm, and capacitive susceptance per phase Vc equals to 3.1416 into 10 to the power minus 4 mho. Now we shall calculate capacitive reactance per phase. Xc equals to 1 upon Vc, that is equal to 1 upon 3.1416 into 10 to the power minus 4. That gives us 3183 ohm. Now we shall determine Zh minus J times Xc. Using values we get 7.5 minus J times 3164.15 ohm. This may be written in polar form as 3164.16 ohm at an angle minus 89.864 degree. Using values we get ICO equals to 89,740.68 at an angle 5.435 degree divided by 3164.16 at an angle minus 89.864 degree. That gives us 28.36 ampere at an angle 95.299 degree. We have computed capacitive reactance per phase Xc equals to 3183 ohm and no load capacitor charging current ICO equals to 28.36 ampere at an angle 95.299 degree. Now we shall determine no load receiving end voltage per phase. VRO equals to ICO into minus of J times XC. Using values we get 28.36 at an angle 95.299 degree into 3183 at an angle minus 90 degree. That gives us 90,270 volts at an angle 5.299 degree. Now we shall determine voltage regulation, that is equal to VRO minus VR divided by VR. We have obtained receiving end voltage per phase on load VR equals to 76,210 volts. Therefore, voltage regulation equals to 90,270 minus 76,210 divided by 76,210. That gives us 0.1845 per unit or 18.45%. So today we have solved one numerical problem on three-phase medium length transmission line. By solving this problem, we have learned how to determine percentage voltage regulation of a three-phase medium length transmission line using its nominal T equivalent circuit when load details and values of transmission line parameters are given. Hope this lecture has been useful for you. If you have any suggestion or question, please drop it in the comment section below. If you have liked this video, give it a thumbs up and share it with your friends. Thank you.